Hello everybody. So in part 2 we are going to discuss the important laws which governs UV visible spectroscopy. So Lambert law. So Lambert law says that when a monochromatic light passes through a solution, the rate of decrease of intensity of radiation is directly proportional to the thickness of a path length. So in a simplified way, you can explain. So the absorbance is directly proportional to the path length of a cuvette cell. And you can see, so this is incident light. So this is incident light, it is I0, and this is a transmitted light. You can say 80. And this is the path length of a cuvette cell. So according to Lambert law, when an incident light passes through a solution, the absorbing species in a solution will absorb some sort of radiation from the incident light. That is actually depend on the path length of a thickness. So this is a Lambert law and Beer law. So Beer law says that the decrease of intensity of radiation is directly proportional to the concentration of a solution. Can say the absorbance is directly proportional to the concentration of absorbing solution. So this is a combined Beer-Lambert law. So the absorbance of a solution is directly proportional to the concentration of the solution as well as the path length of a cell. This is a mathematical representation of Beer-Lambert's law. So A is equal to log of I0 by IT is equal to epsilon into concentration into length. For example, we can say this is incident light. So this is always 100% before passing through the solution. And if the absorbing species will absorb, I can say 20% of light, then IT will be 80. So this is an intensity of transmitted light. This absorbance depends on the concentration of a absorbing species in a solution as well as the path length of a cell. This is Beer-Lambert law, where A is the absorbance and I0 is intensity of incident light. This is 100%, and IT is the intensity of transmitted light, that is after passing through the solution, and epsilon is the molar absorptivity or molar extinction coefficient. This is the unit of epsilon, and C is the concentration of a solution. It can be expressed mole per liter or mole per decimeter, and you can say L is the path length, so it is usually expressed in centimeter. So you can see, this is absorbance versus concentration graph. So you can see the linearity between absorbance and concentration, and you can see here there is some deviation. So what causes this deviation? We'll see. So there's a limitations of Beer-Lambert law. So Beer-Lambert law is applicable only in the presence of monochromatic light. If it is polychromatic, then Beer-Lambert law will not obey. And also it is only applicable for dilute solutions at very low concentration. It is not applicable for solutions of high concentration because there is an electrostatic interaction between molecules when there is a close proximity. And also if there is any particulates in the sample, then Beer-Lambert law will not obey. And if there is any change of refractive index of a medium, then Beer-Lambert law is not obeyed. And if there is any fluorescence or phosphorescence property protein sample. And also if there is any tautomerism like keto tautomerism and there is a equilibrium between two difference, that is keto form and enol form, then Beer-Lambert law will not obey. And also if there is any association or dissociation between a solute and solvent, they will form a complexes through association or dissociation, then also Beer-Lambert law will not obey. So these limitations are very important because there are few questions asked in CSIR, GATE and IIT JAM examinations on limitations of Beer-Lambert's law. I will explain in the problem section. And the important terminologies in UV visible spectroscopy: chromophore, auxochrome, bactochromic shift or red shift, hypsochromic or blue shift, hyperchromic shift, and hypochromic shift. So I will explain these with examples. So first, what is chromophore? So chroma means it's a color, phore means bearing, and it is a part of the molecule which when exposed to visible light will absorb and reflect a certain color. And this chromophore is responsible for color of a compound. So it should contain one or more unsaturated group. There should be some. Okay, I will explain the examples. You can see. So unsaturated group, that is carbon carbon double bond, alkynes, a cyanide group or carbonyl or azo. You can see nitro, carboxylic acid or amide. That should be there. And these are all example of chromophores. So here I have given some chromophores, and this is responsible, and you can see the lambda max value for the chromophores. Then auxochromes, auxo means increase, in Greek it is increase, and it is a functional group when attached to chromophore. It changes both lambda max and the intensity of absorptions. So an auxochrome does not itself absorb any radiation. So it will change the wavelength, its lambda max and intensity of absorption when it is attached to a chromophore. So this auxochrome possesses lone pair or unshared or non-bonded electrons so that it can interact with the pi electrons of the chromophore, and there is a n-pi conjugation. Thereby it alters the wavelength and the intensity of absorption. These are all the common examples of auxochromes. You can see amines or hydroxyl compounds or alkoxy or thiol. So they are the example of auxochromes. So these auxochromes does not itself absorb any radiation. You can see there is no conjugation in auxochromes. But when we see in the chromophore, there should be some conjugations, that carbon-carbon double bond is there, unsaturated group was there. But here you cannot see any unsaturated bond in amines, hydroxyl or alkoxy or thiol. It only alters the wavelength and intensity of absorption when it is attached with the chromophore. Here you can see benzene, the lambda max value is 255 nanometer. Phenol, you can see this is in all the cases this is same. Benzene ring is same, and you can see hydroxyl group, then lambda max will change. If it is phenoxy O minus ion, look at the lambda max value. If it is aniline NH2, you can see lambda max value. Then these are called auxochromes because it changes the lambda max value, and these are called chromophores. Okay, so the chromophore is actually responsible for color of a compound. The auxochromes are responsible for the enhancement of lambda max value and the intensity of absorption. So in the example, this is modern yellow, that is azode. Can you guess which is auxochrome and chromophore? So chromophore means there should be some unsaturated bond. Hence, so this is chromophore. You can see N double bond in. So it's a chromophore, and these are all auxochrome. And in this example, this is anthraquinone dye. You can see this is auxochrome, the blue, and you can see this is chromophore. And various shifts in UV visible spectra. You can see. So if there is increase in the lambda max value, then it is known as red shift. If it decreases, then it is known as blue shift. And the absorption intensity, if it is increases, then it is hyperchromic shift. If it is decreases, then it is hypochromic shift. So hyperchromic, there is an increase in absorption intensity. Hypochromic, decrease in absorption intensity. Bathochromic or red shift means, you can see red shift increase in the lambda max value, that's increase in wavelength. And hypsochromic means blue shift, that is a decrease in wavelength. So these are all very important terminologies in UV visible spectroscopy. Thank you so much. So please subscribe to my YouTube channel for more updates. Thank you.